First of all, do you have any questions? Please don't be shy.
I have all kinds of questions. And you can work in the last 5 homework problems very slowly, very neatly,
Okay.
please. Because if I'm gonna write them down, it needs to be like that.
That is true. The homework is not due until the end of next class, right?
Yeah.
So what about instead of working on the homework problems for you, what about if I give you some hints? That'd be helpful.
Sure, anything?
Yes.
Anything? Okay.
Doors are gone.
Go your way. Now, before we jump into this, I had a suggestion before class that some of you would like to come early and take the quizam before the class starts. That's fine with me if you want to do that. Probably start around 4:30, something like that would be fine. Earlier if you really want it, just let me know. But,
How are we gonna get in here? Because this is a class right up
it
until.
won't necessarily be in here, we'll have to decide where to have it. It depends on how many people want to do it. I've got 2 people so far that are interested.
They usually finish a few minutes early, but not nearly enough time for a full
Okay,
exam.
so I've got 4 people so far. Anyone else interested in that?
I'll consider it, I'm not sure.
Consider it, I'm not sure you're also.
Did you already tell me?
I'm sorry?
Did you already tell me?
No. Okay, so 6 people or so maybe interested, that's fine. And then we have our regular exam at the last half hour of the class. It's fine with me, I don't care. I know that when we had the quiz at the beginning of the class, a lot of people got done in 5 or 10 minutes and then they had to sit around for 20 minutes. And that's why I moved it to the end of the class. If the problems are getting tough where nobody finishes early, then we could have it at the beginning of the class if you guys want to go back on it. But I'd rather just have the option of doing it early.
But you can't give us extra time if we're taking the beginning of the class, right?
Well, my plan is to give you 5 extra minutes anyway, because that's about what I do at the end of class. And then however much time I give the pre-test people, and I give the exact same to the post-class week.
Do we have a quiz in this week?
The plan, I think we decided not to have one this week, right? We had one last week, but chapter 5 is in depth enough that we decided we needed 2 weeks to get that done. So we'll wait until next week to have one for chapter 5. Anything else? Okay, well, let's see. I do want it to be a common starting time if possible. Those of you that came to it, what time did you say you can start?
I'll start 5 for sure.
At 5 for sure? 5, okay.
Yeah.
So let's just plan on 5, okay? So our official start time will be 5 before the class, and 7:30 for after the class. Let's see. Now, you'll have to remind me, what are the homework problem numbers near the end of the chapter?
121, 123, 134, 139.
So 121 is the first one here. Let's start there.
And I believe last class we worked through 123.
Yeah, okay, thank you. You worked homework problems through one?
No, we worked homework problem number 123.
All right, thank you. All right, so 121, let me read it quickly. A 2 cubic meter rigid tank initially contains air at 100 kilopascals, 22 degrees Celsius. The tank is connected to a supply line through a valve. Air is flowing into the supply line at 600 kilopascals, 22 degrees Celsius. The valve is open and air is allowed into the tank until the pressure in the tank reaches the line pressure, at which point the valve is closed. A thermometer placed in the tank indicates that the air temperature at the final state is 77 degrees Celsius. Determine A, the mass of air that has entered the tank, and B, the amount of heat transferred. Well, all these kinds of problems are solved the same way. You have to somehow account for the amount of energy that goes into the tank and the amount of mass that goes into the tank. So you're always going to use a mass balance and an energy balance. Frequently, what you'll do is you will figure out the amount of mass before and after, and that's the case in this problem. You're going to use the ideal gas law to do that. So P1 V1 over R over T1, P2 V2 over R over T2. And when I did this, let's see, what did they give us? They gave us the volume. So does the volume change from state 1 to state 2? It can, it's a rigid tank. How about the pressure? What's the initial pressure? Well, they gave us that, 100 kilopascals. What's the final pressure?
600.
600, right? Because there's no way it can be anything else, right? It can't go above the line pressure, that would happen. Okay. The initial temperature they gave us, the final temperature they gave us actually. So there's nothing here we can't find out. So in the spirit of giving you hints, let me give you the mass you should come up with. 2.36 kilograms is what I've got for M1 and 11.95 kilograms. These are rounded off numbers, so I'm going to put the total on. Okay. So those are the masses you should get. So then it's pretty easy to come up with how much mass flows in. In fact, you guys can tell me, what would you do with these two numbers? Figure out how much mass comes in.
Okay.
Take the difference. Do you notice that that's the first thing they asked for was the mass? Why would they ask for mass first? They're trying to help you out. Make sure you solve it in the right order.
Make it feel good.
Well, make you feel good because that's the easy part, but also because you're going to need that information. Why would you need the amount of mass that goes into the system?
Because mass carries energy.
Because mass carries energy. That's right. In fact, mass carries energy in and it holds the energy. Okay? Now, the problem is that not only do we have mass flowing, but we also have heat flowing. We put a valve in here. So not only is there mass flowing, but there's also heat flowing. And they didn't specify whether it was in or out. I'm going to have to assume direction. If I calculate that the heat transfer is negative, I know I assume the wrong direction. Now, I assume that you started this problem?
1.1.
Who was it that asked about 1.1? Maybe it was just the first one. Okay. First one of the last week problems. Okay, so anyway, anyone, how would you write an energy balance for this? Where are the energy flows?
I did started to, actually, hadn't got,
Sure.
I ran out of time.
Yeah.
But I was thinking it would be, Q out plus M H I on one side, and the other side would be M2, U2 minus M1.
Very good. That's right. Now you have to be a little bit careful here, because did you have Q in or Q out?
Q out.
Okay, if you had Q out, think about it. The mass coming in is a deposit. The Q out would be a withdrawal, so you need a negative sign. Okay, so that's a good observation, but basically you had Q in plus forward carry. It doesn't matter, whichever one you
Yeah,
want.
because when we set the one to zero, then it would still be negative.
Right, right. Well, you just have to be careful, make sure you know what you're talking about. If I wrote Q in here, I'd leave it positive, since I'm assuming an out direction, I'd make it negative. So basically, we need to have everything plug in here. Now, you guys already told me you know how to get the amount of mass that flows in, it's just different from those two. That's a mass balance. You told me you know how to get M1 and M2. Now, where did this come from? Anybody, somebody that doesn't understand this, please raise your hand. Somebody that don't think you can come up with this. Okay, good. Well, let's talk about it. The key to this kind of problem, because if you're saying this, half of the class is saying the same thing, they just weren't brave enough to raise their hands. Half of the problem is realizing that all you have to do is account for transfers and changes. All the transfers added together equal the change. Does that make sense? Okay. So there's a transfer of heat out, that's a withdrawal. There's a transfer of mass in, that's a deposit. And that changes the amount of energy in the system. So that's the first key. Now the second part to this, okay?
I just want, did you all find a key out in the field thing change?
Look to the right of the trailer more. I saw some
I
keys.
lost my
on there.
keys outside. So that was one too.
Look on the
Sorry
right,
to interrupt.
the right side of the trailer, sorry.
No problem. I thought he was coming in and patiently waiting to say, your car's on fire. Didn't want to interrupt. Okay, so anyway, but then the devil's in the details, right? How do you write down all this stuff? Well, Q in or Q out is pretty easy. That's not so bad, right? But over here, how do I know that it's mass times enthalpy? I know that because I know that mass is going to come in, and this tells me how much mass comes in. And I know that that mass is going to carry energy, and this tells me how much energy each unit of mass, each kilogram that comes in, is going to carry. That's how I know to write this down. Now, why did I use enthalpy instead of internal energy? And could there be anything else here?
We use enthalpy because that's what's coming in, but there's no enthalpy when it's in its final state.
That's right. In other words, there's flow energy coming in here, and there's also thermal energy coming in, and I have to count for both, right? This is like saying I've got dollars and cents coming into the bank.
So enthalpy counts for the internal energy.
That's right. It counts for the internal energy and the flow energy. Now, could there be other terms here? Sure. If it was significant, there could be a GZ term, right? That would add to the enthalpy. So it could be plus GZ, plus even some kinetic energy, right? Because if there's some significant velocity coming in here, that also represents energy. And like I said, most of the time we neglect these two, and that's all you need is the enthalpy. Okay, so let me get rid of that, since we don't need it. But all these terms would be multiplied by the mass flow rate, because each of these terms talk about a form of energy that the mass carries per unit mass. It's kind of like having a bunch of people walking in here carrying buckets full of energy, right? Each person carries a certain amount. They're all evenly distributed, so. Does that make more sense now how I came up with that piece? Now how about on this side? What do we do here? Well, on this side, the only thing that can hold energy in the system is the mass. That's it. There's nothing else in here that can hold energy. There's no transfers over there on this right-hand side, so there's no heat or work to include. There's just the energy being held by the mass. What forms of energy can it carry? Well, it could hold potential energy. Could it hold some kinetic energy? It depends on how we define the system. The system could end up moving, and so yes, it could hold some energy. But most of the time, even if the system were moving, it would not be of interest. It would be negligible. So thermal energy, or in other words, temperature is the way I think about it, is about the only thing that can be held. Yes.
Mass 2 in this one is mass out,
M2 is right here.
or just mass in state 2?
The mass in state 2. Good question. The mass in state 2 and the mass in state 1 just refer to how much mass is in the container. I guess I should show you what the system is. That might help. That just refers to how much mass is in the system before and after this whole transfer takes place.
And the other is mass in state 1.
Mass M1, U1. So now the name of the game is coming up with all these pieces, right? If this is the one that they've asked us to find, heat transfer is one of the things they want us to find, we have to somehow come up with the enthalpy and the internal energy in the two states. Now we can't do something like this, MCV T2 less T1. The only reason we can't do it is because the mass is not the same in the two states. This won't work. But what we could do, this is a very common trick with when you're dealing with an ideal gas and you've got an unsteady problem. The trick is we can approximate this as M2 CVT2 less M1 CVT1. This is a trick. Okay? Why is it a trick? Why do I call it a trick? What we're doing here is we're saying the change in internal energy from a particular state. What particular state? Well, when the temperature is 0, we could surmise that the internal energy is 0. Would that make sense? If you could ever get down to 0 Kelvin, then that mass would have no energy. Right? So, what that means then is the internal energy in state 2 less the internal energy at a temperature of 0 equals the heat capacity at constant volume, because remember CV goes with delta U, times the temperature at state 2 less the temperature when the temperature is evaluated at 0. In other words, 0. Okay? So all we're saying here is that U2 can be CVT2 if we take the reference state to be at 0 Kelvin. That's all we're saying. Okay? You can do the same thing on this side with the enthalpy. What's the difference though? If I want to write H1 using the same idea, I would say the enthalpy when the temperature is 0 is 0. So Hn would be equal to what? Enthalpy goes with what? Cp or Cv? Cp. Times what?
I was thinking to change the temperature.
It wouldn't be a change in temperature. Well, it would be. The temperature less 0. Because once again, we're gonna have that zero reference state where the enthalpy is zero. Does that make sense? Right, each evaluated IT equals zero. Does that make any sense? Yeah. Question, comment?
I was just trying to, I couldn't tell what you're writing. Yeah. Was CV times T, no, up one line to the right.
CV, T2 less T evaluated at zero.
Oh, right.
So
Okay.
that's why it's zero, at a temperature.
Okay.
Yes, sir.
Yeah, I just punched it out using the ideal values. The,
Ideal gas
Ideal
values?
gas values.
That won't work. You know why? You can't guarantee that they have taken the reference state of zero internal energy and zero enthalpy at zero Kelvin.
Plus 5 kilojoules off.
Try it with the reference state being a temperature of zero. Yeah, what Mr. Blackman just suggested is we've got a table with properties of air. Why can't we just go back to that table and look up the internal energy and enthalpy? The reason you can't do that is because the only way we can use CVT for these two and CPT for this one is if we take the reference state at a temperature of 0 Kelvin. Otherwise, it doesn't work. Because it's not really true that CVT is U. That's not true. It's delta U equals CV delta T. Okay. Well, that pretty much gives you how to solve the whole problem. Find the mass, find how much mass comes in, or the mass in both states. You find how much mass comes in, you write the energy balance, and you solve for Q out. You get a negative, you know that heat was transferred in. You guys think that heat was transferred in or out of this system? What do you think? Why would you think that? Just a guess, 50-50 chance, or what do you think? The temperature rises, so you think that heat was transferred in. Okay? That's a reasonable guess because the temperature rises, so I understand that. My guess is that heat was transferred out. Now, how is it possible that heat could be transferred out and yet the temperature goes up? Pressure? What pressure? What part of pressure? You're close. You're warm. Bad pun. What's that? Enthalpy change, you're warm also. Once again, what forms of energy does the mass carry in? It's the flow energy and thermal. All right. What form of energy can be held here? Thermal. Where'd the flow energy go? Changed into thermal. It didn't change into heat. This is the only heat. Okay? Changed into temperature or internal energy. Does that make sense? So the temperature actually can go up here above the supply line temperature because of that, because of energy conservation. So when you said pressure, if you said PV, you'd be talking about flow energy. If you said enthalpy, Mr. Beck, then I was thinking, yeah, that's right, because flow energy is a piece of enthalpy. Find your keys?
In what world do you walk by a set of keys and say, oh, look, there's a set of keys laying in the dirt, and then just keep going?
In panic world, probably.
I didn't know who they were.
I mean, yeah, I found them.
Okay.
He knew exactly where they were. He had seen them at some point and just, I probably stepped on them and put them a little further in there.
Oh, I thought you were the one that found them and walked by them.
No, I was the one that was out there looking for them.
I see, so
Yeah.
someone else.
And he had, yeah, apparently at some point.
I saw him and just left him lay there, yeah.
Yeah, didn't say,
Yeah, be asking for you about what's
he didn't like,
last.
we pick up the keys and say, hey, are these any?
They picked them up and nobody was there.
Maybe something.
Then
No,
when
we
they
were all
went
out
back to look for them, though.
Yeah, we were all out there though, and under the circumstances, it seemed like, you know, I don't know. somebody-
All right, is that any help for problem 121?
So,
Okay,
What's the next one?
Hey, I get to this one.
123.
good.
I think we worked that one class, didn't we?
Yeah.
Okay, so what else?
134.
You guys want that one?
It's not fair.
Where's that?
You got it worked out?
Let me just
All right, the air release flap on a hot air balloon is used to release hot air from the balloon when appropriate. On one hot air balloon, the air release opening has an area of a half a square meter, and the filling opening has an area of 1 square meter. During a 2-minute adiabatic flight maneuver, what's an adiabatic? I don't know, it just means no heat transfer, so you make a problem sound like. No heat transfer, maneuver, or whatever that looks like. Hot air enters the balloon at 100 kilopascals and 35 degrees Celsius with a velocity of 2 meters per second. The air in the balloon remains at 100 kilopascals, 35 degrees Celsius, and air leaves the balloon through the air release flap at a velocity of 1 meter per second. At the start of this maneuver, the volume of the balloon is 75 cubic meters. Determine the final volume of the balloon and work produced by the air inside the balloon as it expands the balloon skin. It's kind of an interesting problem because my neighbor, I live out Charlestown where there's a little more space. My neighbor has about 5 acres of space behind his house. Now, for whatever reason, a hot air balloon decided to land in his space. Now, it's kind of odd because just behind me, you get to wake up the llamas every morning if I want to. My neighbor has about 65 acres, a bunch of llamas, and I learned something interesting. You guys probably know this, but I didn't know it. But he had cattle. It turns out that we've got coyotes out there, and the llamas will actually kick the coyotes and keep them away, basically protecting the cows.
Or bite them.
What's that?
Or bite them.
Or will they bite them? Really? Interesting. Okay. So anyway, why they didn't choose to land in 65 acres and they landed in 5, I don't know, but it's cool because I got to look out the front of my house and see this balloon that was landing. Now, I've never taken a hot air balloon ride. Anybody in here done that? Well, what was it like? Did you like it?
Felt like I was high.
Felt like you were high.
It's a different experience.
Was it fairly relaxing or exciting, or what did you think?
I mean, it's like taking off a plane, but really, really slow.
It's not like an adrenaline rush, like, you know.
That's kind of what I thought. I went parasailing once where, you're basically strapped to this big kite. They pull you on a boat. And I thought, oh, this is going to be thrilling. No, it was nice. It was a nice flight, but it wasn't terribly exciting.
When you lift, it's exhilarating.
Actually, it wasn't all that much. It was like, okay, here we go.
It
I guess I
wasn't
trusted
me,
it.
it was like you were just going along and then you catch an air current and you go fast.
We must have not caught a real big
We
air
did,
current on that.
We would do that.
Did you?
Yeah,
Okay.
we would rise.
Well, finally, they decided to keep it interesting. They dip us in the water, and they did. And even that wasn't terribly thrilling. I don't know why. But anyway, it was nice. I would recommend it if you ever get the
I
chance.
bet
It
Billy
was
saw some
fun.
keys up there from that hot air balloon.
What's that?
I said, I bet Billy saw some keys up there from that hot air balloon.
Norm seems kind of sore about that.
I walked up and down that field 4 times.
I have a good lay of the land out there in that field now.
Latch your keys.
All right, so anyway, hot air balloon. We'll draw a sketch of this thing. Here's the balloon skin, whatever it looks like, I don't know. Something like this. We know, I'm going to take the system to be everything inside of the balloon. So we're going to have flow in here and flow out here. Is this an unsteady problem? No. Not as unsteady as you can get. Not as unsteady as you can get, that's right, because we have mass entering and mass leaving, but I guarantee they're going to be at different rates, right? Because if the temperature is the same and the pressure is the same at both points, but the area is different, the only way they could be the same is if the velocity out was a whole lot higher than the velocity in. But it turns out the velocity in is actually higher than the velocity out. So we know that the volume is changing. Now, let me write this down. Initially, the volume is 75 cubic meters. We know throughout the entire maneuver, the pressure is 100 kilopascals, and we know that the temperature is 35 degrees Celsius. If you ever get the chance, another thing I saw that's interesting, probably most of you have seen this, but at times around the balloon races, they'll land somewhere. And last time they did it, that I was in Charlestown State Park. And they didn't even land, they would bring their balloons out, and all they do is fire up the flames. And it was neat because you'd see, at nighttime, you could see the flames through the skin shooting out.
You ever been to
Blue
Heritage
Glow.
Weekend?
Blue glow, that's it.
You ever been to Heritage Weekend?
No, where's that?
Right at Lansville?
How is it? What do they do?
They have every year Heritage Weekend, they always have one of
Is
those.
that one of those? It was neat, it was worth seeing. And it's kind of scary, because if you're close to one and like pull that valve, it's pretty loud. And I mean, you've got a pretty decent flame coming out of those things, so. Anyway, so the amount of time that elapses here is 2 minutes. I just went ahead and converted that to 120 seconds, because I figured I'd need it in seconds anyway. Now, they told us an important thing. They said there's no heat transfer. Is this a realistic problem? Maybe, maybe not, I don't know.
Pretty good skin.
Yeah, pretty good insulation on the skin. Anyway, the inlet area is 1 square meter. I'm gonna make this subscript N. And the area out is a 1/2 square meter. The velocity coming out is 1 meter per second. The velocity coming in, 2 meters per second. Now, what are the 2 equations we use on all unsteady problems? Energy balance and mass balance. Right? There will always be an energy balance and a mass balance, because you got to know how much mass goes in. Why do you need to know that? Because you need to know how much energy. You also need to know how much energy is carried out. Okay, so if we were to write the mass balance, we could write it like this. The mass in state 2 less the mass in state 1 is equal to the mass that flows in less the mass that flows out. Right? Okay, now we might modify this in just a second, but for right now, conceptually all we're saying is that the amount of mass in this system changes because some flows in and some flows out. If you want the difference between the initial amount of mass here and the final amount of mass here, well, then we'd have to write this equation to account for it. Okay. Now, let's see what we can do with this. Because it seems to me that we might be able to somehow get at how much mass flows in. I'm not going to follow the solution I wrote down before. It's pretty in-depth, and there's a lot of simplification, so I'll try to avoid going through everything to make this overly complicated. I'll try to solve things as we go. Because if you think about it, you know the initial volume, you know the pressure and temperature throughout the entire process. Because I think they told us the temperature was constant. So it's constant temperature. Now, that's not because of the 80 bag. That's because they just told us it was constant.
Yeah, when you have like a, if you keep constant pressure, even though you know you're going to have more mass in the balloon than what you're going to have, so that makes your work won't happen.
I think so. I think the balloon's going to expand. I think the volume's going to get bigger, and that's going to be boundary. So we need to somehow deal with that. Does that make sense? Okay. So let's see what we can get at. First of all, getting the mass in state 1 shouldn't be too bad, because we got PVT. All right, so the mass in state 1, if we rearrange the ideal gas law, PV equals MRT. Well, then what we'd have is P1 V1 over R over T. Okay? Now, once you calculate, I don't think I actually calculated the mass in state 1 initially. In fact, it looks like I really didn't finish this problem because all I did was write out all the equations. No, I did. I just kept everything going through. So let me solve this problem without. It became overly complicated because I didn't solve for any of the intermediate results. So I'll probably need some calculator help here, but I want to give you guys more than just some hints. 100 kilopascals times 75 cubic meters. The gas constant for air is 0.287 kilojoules per kilogram per Kelvin, if I remember right. Okay, the temperature in state 1 is 35 degrees Celsius. We need to add 273. Why? Because we're dealing with the ideal gas law. Okay. By the way, as I thought would happen, a few people on one of the exams tried to use the ideal gas law on a liquid. It's called the ideal liquid law. We still have a few people in the class. We still have a few people in the class that haven't taken the exam, so we won't talk too much about it.
Gas.
Gas law, that's right. Got it. Okay, so anyway, now the mass in state 2, could we come up with that? Well, if I can quantify how much mass comes in and how much mass leaves, then I should be able to plug those in here, which would allow me to get at M2, right? In fact, looking at this velocity and area suggests that I could have a mass flow rate over here, right? Because if I knew the volumetric flow rate times the density, I can tell you the mass flow rate. But if the mass flow rate is constant, then if I multiply that by the amount of time, that'll tell me how much mass comes in, right? If I know the mass flow rate coming in and it's constant, multiply it by, it's just basically saying if you got 2 GPM coming in, and it flows for 2 minutes, you got 4 GPM that came in, or 4 gallons that came in. Okay, same thing here, just in a different language. I thought all of thermodynamics was a different language, it all sounds the same to me. Well, okay, I understand. So how much mass comes in? Well, we need the flow rate. How do we get that? Well, the volumetric flow rate can be written as velocity times area. One of the things I notice the students are struggling with is all the different V's in this class. Let me throw one more at you. You've already seen it, specific volume, right? Velocity of flow times area divided by specific volume instead of multiplied by density equals the mass flow rate. So if we want to know how much mass comes in due to this flow, it's simply going to be velocity of flow, cross-sectional area, divided by specific volume times the amount of time that it flows. Okay?
Is that mass flow rate?
It's not a mass flow rate because I multiplied by time.
But you can get
I thought we did that up
volumetric
there.
flow rate by doing
That's the
area
initial
times velocity, right?
This, okay, I have a bunch of questions. Let me answer them one at a time. Right over here, this is
No.
the velocity
Up higher,
time.
M1,
That's initial mass.
This is the initial mass in the balloon.
in the balloon.
Right,
Okay.
right. And this, see, these are the account balances. These are the deposits and withdrawals.
I thought, I guess that's an MI and not an M1.
This is an M1.
Okay.
So that's the mass of the
MI
balloon.
down
This is
there.
M sub I, or MN.
Okay.
That's why I wrote N instead of I.
Now, the question I had was you can get the volumetric flow rate by volume times, or the velocity times area.
That's right, because if you look at a cross-section and you know the velocity at every point in that cross-section, then you basically know a volume flow rate.
Well, yeah, you just put the units together.
You can, another way to look at it, let's say that the flow rate here is 2 meters per second, right? So basically, if you think about this, a 2 meter length of volume is going to go in there in one section,
Yeah.
right? So how much volume is this? Well, it's 2 meters times the area, which is 1 square meter. And that's 2 meters, that's a speed of 2 meters per second, but also a volumetric flow rate of 2 meters per second, which is what we expect to find by just multiplying those two together. Make sense?
Cubic.
Sorry, 2 cubic,
Yeah.
what did I say?
2 meters per second.
Sorry, 2 cubic meters. It's confusing because it's 2 meters per second flow rate or velocity.
It's
and 2
1
cubic
square
divided.
meter.
Okay. All right, so where are we? Well, the volume flow rate we've discovered, but I'll go ahead and plug it in. 2 meters per second of velocity times the cross-sectional area of 1 square meter gives us our 2 cubic meters per second, divided by the specific volume. We have to figure out what the specific volume is. I haven't figured that out yet. We'll do that in a minute. But this flows for 120 seconds. Okay. So let's figure out the specific volume. Why did I use seconds? Well, the meters per second has seconds, so that's what you were saying. But how are we going to come up with a specific volume of the entering
Is it
air?
Inverse of the density.
Inverse of the density, okay. What else?
Well, it's a different temperature.
Notice they didn't tell us the temperature at the end, or did they tell us the temperature at the end? Yeah.
Yeah.
35 C.
Okay, 35 C. All right.
Could you just do ideal gas again?
We could use the ideal gas law.
Because I don't think it's in the table in the back.
Yeah, I don't think it is either.
Okay. So we want the specific volume. The way I remember this, PV equals RT. I remember density, but we could simply solve for specific volume from this as RT over P.
I keep going to this table.
Well, why would, I agree with you, why would you keep going to the table?
I keep going to the table because I'm stupid. It doesn't give me
That's not
anything
so
ever.
very smart. That's actually smart. We're gonna use that table quite a bit. A lot of you will tend to go to the tables. There's a very good reason for it. The tables give you very easy relationships between pressure, volume, and temperature. It's actually not a bad thing to do. Okay, it's just sometimes it doesn't work.
I kept looking for stuff on the quiz in the tables, on those quizzes.
Sure.
And I mean,
Well, then you see that subscript R on the V and the P. You're like, can I use that for volume? No, you can't. You can't. We haven't come to that yet, okay? We'll come to that a little bit later. Okay, so anyway, where were we? So we need the specific volume. Well, that's pretty straightforward, 0.287 kilojoules per kilogram per Kelvin times the temperature of, I'm tired of writing 35 plus 273. 308, thank you. 308 Kelvin divided by the initial pressure, or the pressure throughout the whole process, really, 300 kilopascals. Okay, so the Kelvin goes away nicely. If you remember, the kilojoules are kilopascals times cubic meters, then you see that the cubic meters go away, and I guess I need a 3 there, not a 2. We have cubic meters per kilogram. That's specific volume. Okay, so somebody throw this in your calculator, please. Let's find out what specific volume I should write in down here.
All right, calculators, I got 0.8840
0.8840.
cubic meters per kilogram.
Good job, thank you. Anyone agree with that?
Yep.
That's good. Wonderful, good work. So the cubic meters, we have a meter here and a meter squared here. That'll cancel with the cubic meters in the denominator. What are we left with? That's kilograms. So we'll plug this into our calculators. I can do the numerator if you guys can do the denominator. That's a 240 in the numerator. 2 times 120. 271. Let's just say 271 and a half kilograms of mass.
I think the balloon's gonna pop.
I don't know. I guess it depends on the material properties of what it's made out of. Okay, how about mass that leaves? Well, calculating the amount of mass that leaves is the exact same thing. So why don't I challenge you guys to calculate the mass flow rate? And well, actually the total mass that leaves. So all of you try to do it individually. You can talk to the person next to you. And let's just see what kind of answers we get. It's actually pretty easy to do once you see the trick.
I just saw the trick here. I have the same thing, but I saw that.
See, we're calculating mass flow rate. What's the 271 kilograms mass in?
That's how much mass comes in that 2-minute period. There's a real easy trick here. Give you a hint, what's the density of the air coming out?
Well, I figured you use the idea of gas law. Yeah. That's what I'm figuring.
Good. You're gonna kick yourself when you see it.
It's just half, ain't it?
Almost.
No.
Not quite half.
67.87.
That sounds right. Anybody see how to get 67.87? That's 1/4. It's a quarter-ish number. How do you know that it's a quarter? Well, look.
Half and half.
Yeah, half and half. The amount of time is the same for both. The specific volume is the same for both. The only difference between the two is the area times specific, or in other words, I'm sorry, I said that wrong. It's the area times the velocity, okay, which is essentially the volume flow rate. So the only difference between these two is we have 2 separate volume flow rates. This one's 2 cubic meters per second. This one is a half a cubic meter per second.
I thought that area, I didn't see the areas were different.
Yeah, so that's you were on track.
It said half a cubic meter per second, so.
Yeah, that is right. A half a cubic meter per
Okay,
second.
so the
And
mass
2 coming in.
half is a quarter, so it's a quarter. That's a quarter of the mass that's in.
Yeah, exactly. Because the flow rate out is a quarter of the flow rate in.
But you could have just done the arithmetic.
You could have gone through it all. You could have done this all over again.
Yeah, because I'm not gonna see things like that ever. I can't even find
Well,
my keys.
You don't have to do that again, since the temperature is the same, right?
Right, you don't have to do this again because the pressure and temperature are exactly the same. And that's why you can look at this and just look at the volume. Basically, well,
Yeah.
that doesn't matter. So the mass that flows out in that same 2-minute period was what? What'd you say, 67 point something?
0.87. It's 7.87.
60.87? Since we're rounding off to the first decimal place, let's just call that 9. Okay. So now could you figure out how much mass there is in the balloon in state two? Sure. Let's do it. Mass in state two is the mass in state one, move it to the other side, plus whatever mass comes in, minus whatever mass leaves. Know the initial mass of the balloon.
I think we would put a value to it.
Okay, I think you guys told me the number, I didn't write it down, I don't know why.
I got 848.45.
Yeah, that doesn't sound familiar, so I guess I didn't ask you guys for it. Yeah, that should be right. We've got kilopascals, cubic meters, which will cancel with kilojoules. Kelvin goes away, so we get kilograms. Anybody verify that, 848?
Yeah, so much.
I got 84.8.
84.8?
Yeah,
that's
that's
right.
what I had to.
I might have missed a decimal.
Decimal.
Or 10 kPa, 700.
Well, does that make sense? Because,
1,000 kPa.
It's the initial.
I think I did 1,000, so.
all right, well, we have more people to say that's right. We'll stick with that. Okay, so how much mass is there in this balloon in state two? About 84 plus 3/4 of that.
288.47.
Okay. Hope the balloon skin can take it, I don't know. We're not up to the balloon, so what difference does
It
it
might
make?
be there now.
The mass at state one was 84.84.
That's what, yeah, that's what everyone got.
Yeah.
84.85 if you round it off properly. That's supposed to be a 4 there.
Okay.
Well, we've come a long way, but we're not even halfway there. Why? Because the mass balance is the easy part. Now we have to use the energy balance. Okay, so let's see what we've got. Let's make some notes. We've done a little bit of work here. The mass in state one before we started all this was 84 point, let me round this off to 85 kilograms. The mass in state two was 288.47 kilograms. The amount of mass that came in was 200, in fact, let's put this with the place where it flowed in. So here's in, 7.9. Okay. Well, help me write the energy balance. How would the energy balance go?
I had a Q in it, billion somewhere, H.
A Q? Would there be any Q?
No, there won't be.
There you go.
No Q. It's not the heat, it's not because the temperature stays the same, it's because they told us there's no heat transfer. But there is boundary work that comes out, that's right. So how would I write this? Since boundary work's coming out, is this a withdrawal or deposit? So negative or positive?
Negative.
Just like your bank account. Boundary work,
What's that?
Plus the sum of the mass
out
in,
to make it very clear. Plus what?
plus the sum of the mass in.
Okay, do we have multiple mass flows in or just a single one?
One.
So we don't need the summation sign, right? So mass in times what?
Enthalpy.
Times enthalpy. Enthalpy of the incoming stream. Good. What else?
Max out.
That kinetic energy.
We do have kinetic energy coming in, that's true. And we could evaluate it. So I think we should probably throw it in there. V n squared over 2. If it gets to be too much work, we can leave it out at first and see what happens. Okay, because this is not a terribly fast stream coming in. Okay, if we compare the magnitude of those two terms, I don't think that it would be appreciable. Anyway, but let's leave it in for now. What else?
Equals.
Well,
No.
before you say equals, there's mass out. Right? So we have to say minus mass out times the enthalpy that it carries and the kinetic energy that it carries. I'm out of space, so we're going to put the equal sign below. Because you have to be careful. You've got to account. If you want to balance your checkbook, I know nobody does that. But if you want to balance your checkbook, what do? Well, you have to subtract all of the withdrawals, right? And you have to add all the deposits, otherwise it's only a balance. So if you miss a flow here, it's not gonna balance.
I go to the ATM and hit balance inquiry.
Yeah, if you do that, you might miss the, I gotta tell you guys, it was
Really, I paid my
4 months ago.
grandmother,
What's that?
I'll page her on her beeper.
Hey,
Apparently it's 1993.
Well, I do online banking, and I'm fortunate because I'm a little bit concerned about all the technology and hacking and all that. And a couple of months ago, I looked on my bank statement. Apparently, I had spent about $500 in Colorado. I've never been to Colorado. So I was very fortunate that I caught.
Isn't it odd how I bought somebody a lot of groceries in Georgia last year.
How generous of you.
I love it. It was like $400 in
Was
groceries.
it for strictly medicinal purposes in Colorado?
No, this was actually at a Home Depot and something else, I don't remember
Been
what.
in new windows.
And you know, what really ticked me off about it is how hard it is to get somebody to investigate this sort of thing. It's actually, you'd think that they would be hounding this stuff down, like, I'm tempted to become a criminal, as easy as it is, you know? I mean,
The credit card stuff's like in banks. I had somebody who spent $1,600 at Abercrombie and Fitch.
yeah.
So do they reimburse you?
Oh, yeah, they reimburse you, but basically what happens is all the costs, all that money gets distributed among all
They
of
pay
us.
$60 a shirt, but-
Instead of catching somebody and putting them in jail, they
Chase,
say, yeah.
Wads are on.
Chase is pretty simple with it.
Chase is pretty simple, what do they do?
You just tell them that you didn't make this purchase and
Well, that's what my
There you go.
bank did, yeah, because it was my debit card, and I said, look, I didn't make these purchases, and I fill out some paperwork, and they gave the money back to me, but.
I didn't have to fill out paperwork.
Oh, really?
Yeah.
With our card, we just sit back, we just called them up, it was like, I don't
Yeah.
know this.
Well, I was just surprised because I even called the police in Boulder, Colorado, saying, hey, will you guys please investigate this? I want the bad guys caught, you know?
Oh, yeah, they'll never, they never like.
They probably asked you if you had
Stop,
any
they cut them off.
purposes.
Yeah, really.
Oh, well, anyway, so where are we? On the right-hand side, so we found a bunch of deposits and withdrawals, so at least, what, 2 withdrawals and 1 deposit. What does that do?
That gets us after there.
Gets us halfway there, it changes the balance of the system, so we better figure out what the balance of energy is. What kind of energy can the system hold?
Thermal.
Thermal energy. Right. We could talk about potential energy, we could talk about kinetic energy, maybe as the balloon moves as a result of this. We don't know anything about it, and it'll be small anyway. So the main form of energy this is going to hold is thermal. How do I quantify, how do I write symbols to talk about the amount of energy in that balloon? What is it?
Mass times it.
Mass, by times enthalpy?
Times
No,
internal.
Internal, that's right. So basically what I will need is the final balance less the initial balance. Does that make sense? Now, what am I saying balance here? Well, you look on, let's say you go to your bank and say, what's my balance? They tell you it's $1,000. You say, okay, you go to the store, you spend $10, you come back to the bank. What are they gonna tell you your balance is? $990, right? Because basically they will tell you $1,000 here, and after all the transfers, $990, I'm sorry, other way around. They'll tell you $1,000 here, and after all the transfers, $990 here. That was a change of negative $10 in your bank account. Not a surprise you withdrew $10, right? So you gotta separate in your mind, think between deposits, withdrawals versus balance in account. Okay? Those two are very different things. I saw confused looks. Any questions? Okay? All right.
I'm confused, I just don't want to ask, so I'm just gonna keep this.
Okay. All right. Well, let's see. Do we know the enthalpy coming in? We know the temperature. In fact, we know that the enthalpy coming in and the enthalpy leaving are the same, right? So couldn't we use CVT if we wanted to, or CPT if we wanted to? So that's something we could do. So we could use CPTN, CPTN. We know the inlet and exit velocity, so everything in the parentheses are just numbers now. We know how much mass flows in and how much mass flows out, so all of this is just a number. Yes,
Why do you use TN for?
Why do we do
Yeah.
Is there equal?
sorry, they're equal. but technically, you're right. No,
Okay.
I thought that, but I saw it, I just thought because they were equal, you.
I don't talk and write well at the same time. That's
But,
all.
okay, so, never mind. I think I did it. If it was different temperatures, you would use the
You
hour
use-
temperature.
Right, exactly. You got it. And so I've corrected it. So this bit here is just a number. How about this? We know the mass in state one and the mass in state two. How about the internal energy? Now be careful here. The internal energy in state two and the internal energy in state one that I'm asking you about is the energy per unit mass. So do you see how those two are exactly the same because the temperature's the same? So this is gonna look kind of strange because it will be M2 less M1 multiplied by U, where we don't really need a subscript because it's the same. We don't usually see that before, right? It's usually M delta U, not delta M U.
But since we have flow energy in, wouldn't the inside fluid get hotter? I mean, we're quadrupling its volume almost.
We are quadrupling its volume, but they told us that the temperature stays the same. There's no change.
There's that.
Well, the fact that there's no heat transfer doesn't mean that it stays the same.
This is the air in the moon remains
38 degrees.
So what you're talking about, all that flow energy that comes in, what it's gonna do is it's gonna come out of the boundary. Okay? All right, now we know the mass in state one and the mass in state two, so that's no big deal. How are we gonna deal with this guy?
Look it up.
CVT.
CVT, why would we not look it up?
Because you're wrong.
Because there's an idea.
Thought you always told us back of
Because-
the book for
Yeah.
thermal energy.
I know. Go to the back of the book, please, and what is that table? Is it A19, I think?
Something like that.
A17, okay, what A17? A17, A17. Yeah.
File reports.
It gives it to us, but the reference state is not necessarily the same as what we want. We want a zero enthalpy, zero internal energy at a temperature of zero. Okay? We don't know the reference state here, they haven't told us. Okay? We can't guarantee that that will work. Now, if I remember correctly, I'm going to go out on a limb here and say that actually the reference date in that table is zero. A minute ago, Mr. Blackman, you said you were only 5 kilojoules
Yeah,
per kilogram or something wrong. The reason for that is because when we use CVT and CPT, we're assuming that the heat capacity is constant. It actually is not constant as you go up and down in temperature. This table takes into account the variation in heat capacity. Okay? But to keep things simple, I want you to think of CVT and CPT because this trick is used so often. Yes?
The question I did have, how did you simplify it from M2 U2 minus M1 U1 to?
Because I recognize that the internal energy in state one and state two are the same per unit.
Is that just because the temperature's the
Because the
same?
temperature's, that's
So
right.
that's how you were able to see
So
that?
because the energy in an ideal gas, the internal energy and the enthalpy depend only on temperature. And that's what Joule's experiment showed. He had a
Yeah.
container of high pressure gas and most of our intuition would say, well, there's some energy in there, there's potential energy. You open the valve, air rushed to the other side, and obviously there's less potential energy because the pressure went down, right? At least that's what our intuition says. And he noticed though that the water jacket surrounding it did not change its temperature at all. And since he already knew that energy was conserved, he knew that meant that the amount of energy in the air had not changed at all. Which is a surprising result, because you would think that as the pressure goes down, that the energy would go down.
I keep using CV delta T and CP delta T. And I don't know if I'm just not using it in the right situations. I mean, I'll have a situation arise in which way is around the homework and.
Well, you have to be careful with it, because CV delta T and and this is something I noticed, there was something, a homework problem or something somehow, where we were trying to calculate an enthalpy change or an internal energy change, something like that. And a lot of people tried to use CV delta T or CP delta T, and it did not work out. Why?
It won't
Well,
work for everybody.
it works just fine for everything. CV delta T, there's nothing wrong with that. But when it does not work is when there's not a temperature change. Like if you have liquid going to vapor, that's a phase change. CP delta T can't say anything about that because there is no delta T. Right? That amount of energy has to be calculated by the phase change energy, the latent heat vaporization. That make sense?
Where do you find that?
It's HFG. You have to find the table. So
That's
like
what I'm-
with steam, you gotta find
Yeah,
out.
there's just some things I'm missing and I'm not
Right.
getting
Well,
the gaps filled in. and see it.
Right, well, this class is all about getting all the little pieces and putting them together in a way that makes sense. And that's not easy to do because you got a ton of symbols that you're not used to seeing.
So
And
what's the
principles
latent heat
you're not used to.
vaporization again, HFG?
HFG is the latent heat of vaporization. That's the amount of energy it takes to take saturated liquid water to saturated vapor. Okay? Now, it's not going to change temperature at all during that time because saturated liquid is just on the verge of boiling, where saturated vapor is where the very last drop of liquid has been evaporated. This is a great discussion. Anything else?
Can you reiterate that pressure experiment?
Yeah, Joule's pressure experiment. Well, basically what he did is he had two different flasks that were connected together by a valve. One of the flasks contained very high pressure air. The other flask was evacuated and had nothing in it. He put water all around it, and then he opened the valve.
Okay,
And-
all around.
Yes, water is all around this thing. So the air is not going to leak out of the combined system of these two flasks, right? But it's gonna go from one to the other. This pressure can equalize. One's vacuum, one's got high pressure. And what you would expect to see from intuition is you would expect to see a temperature change, right? Because you'd expect the air has now expanded, therefore it has lost energy, therefore energy must have come out of it. The only way it could have come out is by going into the water, and the water would respond by increasing temperature. Or the whole thing will explode or something, right? But nothing happened. There was no change in the temperature of the water at all. And so what that proved is that the air still had just as much energy in it, even after it expanded, as it had before it expanded.
Okay, because I thought the water was just covering the high pressure side.
No, it's covering both sides.
Just a few too many times when you're releasing CO2 pressure, you can freeze your fingers.
That's right, and so that's another question. When you take a compressed gas and you allow it to expand, then it actually does cool down, right? So what happened here? Well, let me show you what happened. Let's pause on this problem for just a second and talk about Joule's experiment, because it's actually really interesting. Here's the valve between the two. Okay? Now, if you got high pressure air over here, the air is going to flow over to this side, right? Over here it has internal energy. As it flows, it's going to have enthalpy because it will have internal energy plus flow energy. And as we've discussed, the temperature of this air is going to go down, right? Because this extra flow energy has to come from somewhere, and it comes from this. What's going to happen over here? The temperature over here will look artificially high, U2, let's call this U1 and U2. This one's going to start dropping, this is going to start going up, right? They will exactly balance each other. And at steady state, or at equilibrium, the temperature, basically this gas is going to give some of its extra energy back over to this gas. And the net effect is that there's no change in temperature of the water jet around it. So this will cool down, but this will heat up. So let's say the temperature of the air is at 20 degrees. Well, the temperature over here is going to be more than 20 degrees, and the temperature here is going to be less than 20 degrees at one point in time. But then they equilibrate, and they're both going to come back to 20.
So is it kind of like, thinking about it as almost like you have like water or something and it flows up really suddenly, goes up and then it goes back this way?
Yeah, exactly.
Doesn't
Exactly.
go back to the.
Same thing. Yep. And that's a very good analogy because if you think about potential energy, well, let's see, would that work? I won't go there. I got to think about that a little more before I confuse you and myself. Okay, anyway, so much for Joule's experiment. Any comments or questions on it? Now back to the problem at hand. We've decided that we can use CVT for the internal energy. Since the temperature is 35 degrees, then basically the right-hand side of the equation is known. The only thing that's unknown is the boundary where it comes out. Okay? Now, for practice, I'd like you guys to go ahead and calculate the boundary where it comes out. I'd like you to plug in all the numbers. If we say we can do it, let's do it. And then we'll calculate this another way and see what happens. There's another way to do this. Probably would be a good idea for us to calculate a few of the pieces, like CPT, CVT. Notice those appear in a few places. Maybe the square of the velocity N over 2, the square of the velocity L over 2. Probably mass times enthalpy plus V squared over 2, since we have those terms on both sides, one for the mass out, one for the mass in. So let's get some numbers for all the intermediate results.
CP is 1.005, right? And
That's right.
CV is 0.718.
So, yep.
You can multiply that by the temperature at that state.
That's right. Now, it's not just 35 degrees, it's 35 plus 273.
Yeah, that's what you do.
Or CPT,
Sorry.
Go ahead.
I got CPT.
Okay. You have also?
You got CV?
CP?
CP.
Okay, CV was, I had it.
Whoever has whatever, just tell me. CPT is what?
CPT is 309.54
What are the units?
kilojoules per kilogram.
Right. Kilojoules per kilogram for CPT, because the temperature.
CVT is 221.14 kilojoules per kilogram.
Now, you guys probably recognize that this V squared over 2 term is going to have to be changed, right? Because it's going to be meters squared per second squared, but we really want kilojoules per kilogram.
Which is just 1,000
It's
meters.
just 1,000, that's the difference, that's the ratio. So what else do we have?
VN squared.
V n squared is what?
0.00.
0.002,
Oh, yeah.
and that's converted.
Is that is converted to kilojoules per kilogram? How did you get that? Well, you took 2 squared and divided by 2. So that's 2 divided by 1,000. It's 2 thousandths. Yep, good. Now, what else?
It's gonna be 0.001.
I got
Or
0.0005.
Okay.
305, because it's.
Can you go through that conversion factor again? I know you just talked about it.
Sure. Yeah, no big deal. I'll do it right here. Vn squared would be 2 meters per second, has to be squared, divided by 2. And then there's 1 kilojoule per kilogram
Right.
for each 1,000
Okay.
meters squared per second squared. So 2 squared is 4 over 2 is 2, divided by 1,000 is 2 thousandths. What else? Well, now we've got these pieces. How about either inside, in or out?
Is it, we already calculated it.
Right, I realize, I'm just saying the whole term, mass times enthalpy plus kinetic energy. By the way, did you notice that the thermal and flow energies are huge by comparison? I mean, the kinetic energies are laughable, right? They're so small.
0.0005, yeah.
By comparison to something where, this is in the round off, right? So those really don't matter, we're gonna round like anyway.
So basically, back when you're saying that we didn't really need the velocities, we could have just left those out.
It's not the velocities we don't need, it's the kinetic energies we don't need.
So the enthalpy is the CPT, right?
The enthalpy is CPT, that's right.
You didn't have a pretty high velocity curve.
You would.
CVT is 221.144, so 221.1, yeah. I was just checking it, I didn't know
Okay,
what number, I
sure.
was just checking.
That's fine, no
Yeah.
problem. Okay, so the inlet side, the energy that's carried in by mass, how much do we have? Let's do it this way. $84,040. Okay, what units do you have there?
Should be just kilojoules.
Should be kilojoules, because you got kilojoule, or here you got kilograms per, you might just have kilograms, times kilojoules per kilogram, so this is just kilojoules.
You got 84,000.
Anyone verify that?
I got that, I got the same thing, yeah.
How about energy out? Okay, so now we really do have two numbers here. How about on this side of the equation? How about the M2 less M1 CVT? What do we have there? So notice this is the change in energy of the system. What does that come out to?
You guys think what?
45,030.
Anyone second that?
Yeah, roughly.
Yeah, 45,000, 48.
28 or 30, which one do we
I
want?
got 28.
Which one's more accurate?
I got 28.
28.
That's what I got.
So 45, now that's the change in energy of the system. That's how much the account balance changed here. Okay. Did that account balance go up or down? This is positive. So this says it went up. Which makes sense, right? Because there was a lot of air that came in that carried energy, and not a whole lot of air that left carrying energy with it. Okay?
Could you, would it be wrong to think of it intuitively, like if you had more energy leaving than you had going in to the balloon, would the balloon be deflated?
Well, deflating versus inflating is a question of mass flow, not a question of energy flow. All right, so anyway, where are we? Well, we've got numbers for all this stuff. So basically, the boundary work, or the negative of the boundary work out, is equal to, let's move all the terms to the other side. I guess we'll start with this one. So whatever that is, energy in, that'd be a negative 84,040. Yeah, that takes care of this guy. We move the energy that flows out with mass to the other side, or withdrawal. That would be a plus 21,008, right? Because I have a negative sign here, so when I move to the other side, I have to flip the sign. And what was already on the right-hand side was the change in that. So that's plus 45,028. All these are kilojoules, so I won't bother writing them with each of the terms. All right, so what's the result?
Negative 17,994.
17, how much?
994.
994 kilojoules. Okay? So obviously, boundary workout is about 18,000 kilojoules, right? Because the two negative signs. Okay. Now, we draw this system a little bit differently. Let me draw it this way. This is the system. This is the balloon. Okay. We're going to have a constant pressure. Let me get rid of this complicated looking balloon because we actually don't even need it. Okay. I'll show you a nice trick here. The pressure in this system is constant. It's what, 100 kilopascals? Is that what we were told? The temperature in this system is constant. It's 35 degrees Celsius, which you guys said was, what, 308 Kelvin? Right? The volume was given initially as 75 cubic meters. If we just had the volume in state 2, we could say boundary work is P delta V, couldn't we? Because it's a constant pressure process. Right? So how could we get at the volume in state 2? Well, that's pretty easy. We have the mass in state 2. In fact, the volume in state 2 from the ideal gas law, well, let's just do it this way. PV equals MRT. The only thing that changes is the mass. And so basically the volume in state 2 would be M2RT over E. So go ahead and calculate the volume in state 2.
It's frustrating because I did it this way first time around. And I didn't believe it because the volume and the energy were so high. But at the same end, it was absolutely perfect.
So you know the mass is 288.47? You guys need me to write down the gas constant?
0.287. I
Point
got
two eight seven.
254.99, 255.
I got that too.
254.99, so yeah, 255, let's just call it that.
And that's cubic meters.
Okay. Now calculate the boundary work, 100 kilopascals multiplied by the volume in state 2, 255, less the volume in state 175. By the way, the results are going to come out in kilojoules. What do we get? 18,000 on the nose. How do you like that?
So it's basically chapter 4 probably, right? Let's just cover chapter 4, we won't even.
Okay. So it's a little bit frustrating, but at least it's consistent, right? At least both methods gave us the same result, because they're both right. Okay? So it's a nice check. Now, if you had gone through in your homework, the ideal situation is to work it both ways. One is a check of the other. Okay, remember GFSA-C? We always forget that C part. Check, what's that? Something in the game of chess. Well, anyway, I thought I'd go through that problem because most students will not recognize this as a simple piston cylinder problem. That's all it really is. But it looks more confusing than that because it's this big, real hot air balloon thing. Okay? It really exists, whereas piston cylinders don't. Now, the other thing that's confusing about this is that it's not quite as simple as this. Actually, it's like this. You've got flow coming in and you have flow leaving. But it turns out that doesn't affect the boundary work because the properties of the incoming and leaving stream are all the same as what's inside the system. Okay. What can be a little confusing is, well, since there's a change in mass in the system, can I really use P delta V? Yeah, you can, because all this is talking about is how much work it takes to push this piston and move the atmosphere out. So don't be angry because there's a shortcut something the way you may not have seen. Just realize both are true and not both. I'm going to test you on both. You need one.